I'm going to be going through some of the solutions for the 2019 Term 3 finals for Phys1121 with you. So I'll be covering question 2, part B first. And I'm just going to go from the solutions provided on Moodle. I'll just talk you through it and let you know the logic behind it. But these solutions are mostly correct, so you can rely on them. So for part B first, we just see, okay, so you have a mass that's placed on a platform with a spring, and then you basically compress the spring by 5 centimeters, and then you let it go, and the spring is gonna bounce back up and push this mass upwards. And the observer sees that this mass flies up by 3.5 meters above its release point, and we're supposed to find the speed of the mass just after its launch, and that is just after it lose contact with the spring. So for this one, the easiest way to approach it is use the conservation of energy. So at first, when it's still contacting the platform, it would have like maximum kinetic energy that's being given by the spring. And once it flies up to the maximum height, it will stop before it falls back down. So at that moment, at the maximum height, remember from projectile motions, you have zero velocity. So you have zero kinetic energy, and all of your kinetic energy from the beginning has been converted to gravitational potential energy. So using this, we see the total energy initially equals the final total energy. And from the argument we just went through before, we see that Ui is 0 and Kf is 0. So really all we're trying to do is to equate the initial kinetic energy with the final potential energy. And that's given in this equation here. So you have half mvi squared equals mgh. Bit of simple algebra, rearrange it, and then you put in the numbers and you get 8.3 meters per second, which is reasonable. Okay, and for part 2, what is the spring constant for the spring? And justify your answer. So like we said before, the initial kinetic energy was given by the spring, like unloading. So we can use that to relate the total energy of the box that's flying off with the energy that the spring had stored in the spring potential. So in this case, we assume that all of the energy given to the box came from the spring potential. So the potential energy of the spring is equal to the total energy of the box. And the total energy before, like we said, you can either use the initial kinetic or the final potential. They're both the same. In here, they chose to use the final potential energy, which is fine. So you have the potential of the spring is half kx squared. Now you just rearrange this to get k as the subject, and you get 2 times the potential energy divided by the x squared. And putting mgh, and you would have got that from up there. You got a mass and everything else is given to you. And since the spring was compressed by 5 centimeters, so x will be 5 centimeters, except it has to be an SI if you want the final answer to make sense. So 0.05 squared. And that just gives you 4.1 kilonewtons per meter. I don't know how realistic that is. It's a spring, so it sounds reasonable enough. Cool. Okay, so next I'll be going through question 4 as well. So question 4 is all thermodynamics. Starting with part A, lead shot, so like lead bullets, the old bullets for muskets, used to be made by dropping molten lead from a large height and collecting the resultant ball of lead via a vat of water. And 530 lead shots, each with 5 grams mass, are heated to 345 degrees Celsius, then dropped into a large steel bucket containing 15 liters of water. That is initially at 19.3 degrees Celsius. Assume that no heat is lost, and no heat is lost to surroundings, and no steam is produced. What is the final temperature of the water? Okay, so this is identical to one of the labs you did with melting ice. So you're just gonna, let me just scroll down. Okay, so you're just gonna write down the equation where you set up to have the heat lost by the lead is equal to the heat gained by the water and the heat gained by the bucket. So yeah, it's all pretty simple. So you just have the mass times the heat capacity times the temperature difference for each material. So you have the steel, the water, and the lead. You'll see that the initial and final temperature is like backwards compared to the other ones here is because you would have had a negative sign in the beginning, because this is a heat lost on the left-hand side and it's heat gained on the right-hand side. We just absorbed a negative sign in here to flip the ordering, so this is not a typo. Okay, and the second point you're going to have to figure out is, because they all start with different initial temperature, the final temperature will be the same, because the lead and the water, when they get together, the heat gets exchanged and eventually everything will come to thermal equilibrium. So it's perfectly reasonable to substitute the T final for the lead to be the T final for the water. And once you do that, you realize that everything else is given to you in the question. So all you have to do is just a lot of algebra. It's not the prettiest looking question, but there's no more physics in this. You just rearrange everything, get T final for water as a subject, and then sub in all of the numbers, and pray to God you typed in your calculator correctly, and the final temperature is 21.1 degrees Celsius. Nothing too special about the rest of this question. You just got to know how to set up this first line and understand physically that the final temperature should be the same. Besides that, everything else is just math. Okay, part B. Air is composed of 78% nitrogen and 21% oxygen. Okay, so part 1, to a good approximation, how many degrees of freedom does air have at room temperature? List the types of motion each of these degrees of freedom corresponds to. So at room temperature, they would just have 5. So we have 3 translational. So imagine 3D space, you have X, Y, Z direction that you can move. And because both nitrogen and oxygen are diatomic molecules, so you can have 2 rotational degrees of freedom. So add together, you get 5 in total. 2, a 10-liter container is filled with nitrogen at room temperature and is sealed. What is the average room mean squared velocity of the nitrogen gas molecule? Okay, and you get given the mass. So for this one, you use the equipartition theorem. You know the energy per degree of freedom is given by half kT. And since you have 5, okay, so this solution here is actually not correct, I'm afraid. So as we said in part 1, you have 5 degrees of freedom, so it should be 5 on 2 kT here. So yeah, you use equipartition theorem, get this amount of energy for each degrees of freedom, and you equate that to the kinetic energy, and that relates the velocity to the rest of the equation. So here, if you just change that to 5, because you have 5 degrees of freedom, 5 half kT equals half mv squared. Rearrange that. The root mean squared velocity is just v squared. So then now this will be 5 instead of 3 here. And you'll get a different numerical answer because of the change in the degrees of freedom. But physics is the same. Okay. And for part 3, the gas is now excited by radiation and breaks the bond and causes the nitrogen to become monatomic. While maintaining a constant temperature, what is the average room mean square velocity of the nitrogen atoms? Okay, so 2 things actually happen here. So, okay, again, the solution's a bit incorrect in the explanation. So, once you break the bond, they become monatomic atoms. You no longer, you can imagine like a ball. If you can't see it spinning, then it's moot point to talk about the rotational degrees of freedom. So you actually lose 2 degrees of freedom in this case. So you're down to 3 translational degrees of freedom only. And the other changes now, each one of them, because only half of the original N2 molecule, you also have only half the atomic weight, so only 7 atomic units. So you do the exact same thing, except you now actually, okay, so they got it right by accident. So you do the same thing with 3 degrees of freedom, and then you have the mass to be half of what you used in part 2. And, well, in this case, this will be actually the correct answer because they made a mistake in part 2 and used the same answer for this one. So carry on, accidental mark. I don't know. Okay, so for part C then, classic PV diagram question. These ones are, you can pretty much bet there's going to come on, and the process is usually the same to do these questions, so kind of a free mark. So the diagram shows a cyclic process. So go from A to B to C to D. So these 2 are isobaric processes, and then you have B to C, which is adiabatic, and then D back to A is isothermal. And they give you a whole bunch of other information like the heat loss, the heat gain and heat loss in the two isobaric processes, and also all of the state variables, so the pressure and volume at each of these points. Okay, for part one, calculate the work done on the gas as it goes from state A to state B. Okay, so the work done, you know the equations like, was it integrate P dV or whatever, but if you think about it, if you have a straight pressure line, then the integral is just asking for the area under this curve, which is a rectangle. So you don't go on and actually do the integral. Well, you can, but it would just be taking longer than necessary. Just work out the area of a rectangle. So you have the height, which is 2 atmospheric units though, so you're going to have to multiply by 1.01 times 10 to the 5 to get it to SI, and times by the width of this rectangle, which you are given all the state variables, so you can work that out pretty easily. So 4 minus 1.5. So yeah, you get the area, and it's 505 joules, kilojoules. And yeah, careful with the sign as well. So okay, part two. What is the change in internal energy as the gas go from state D to state A? Now, state D to state A, as we said before, is isothermal. Change in internal energy requires a change in temperature. So in an isothermal process where temperature is constant, you wouldn't have a change in internal energy. So it's just zero by definition. And yeah, that's exactly what we have here. Okay, part three, what is the change in internal energy as gas goes from state B to state C? Okay, so this one is the adiabatic process, so it's not so straightforward. And the way to approach this is actually to calculate the heat, the change in internal energy for every single process, and then taking advantage of the fact that we know when you go around the entire cycle, the change in internal energy is zero, like a conservation of energy idea. You're not supposed to lose anything. So in this case, we know delta E around the whole cycle is zero, and D to A was also zero because it's isothermal, as we said before. So all we're going to find out is the change in internal energy for the A to B and C to D. And using the first equation, then we can find out indirectly what the change in internal energy from B to C is. So the change in internal energy, by definition, is heat plus the work. And we can work out the work. We can calculate the work, no pun intended. For A to B and C to D quite easily, as I said before, it's just the area under the curve and it's just rectangles. And we're very lucky they gave us the heat entering and exiting the system in those two processes. So just put in the numbers, 505 kilojoules before and then 1270 kilojoules entering. So in this case, we found out the change in internal energy A to B is 765 kilojoules. Same process for C to D. You get given the heat exiting, you find the area under the curve, and you get minus 333 kilojoules. So this plus the change in internal energy from B to C should all add up to zero. So with simple algebra, you put them together, then you find out that the change in internal energy is minus 432 kilojoules. You can also do this other way, but I think this is the most logical way to think about it, and it's not that much work considering you already did part one for half of it. So finding areas of rectangle is not algebraically intensive. Cool. Okay, so last one. Part four. Write down an equation relating P and V as the system goes from state B to state C. You should calculate as many constants in equation as possible, given an explanation of how you calculate each one. It sounds very complicated, but we all know what the equation relating P and V in the adiabatic process is, and there's only two constants that we really have to calculate. So yeah, PV to the power gamma is equal to some constant. So I guess in this case we have to calculate this gamma and this constant. Well, the gamma is given by degrees of freedom, so you don't actually have to calculate it with at all. Is by definition what? Okay, did they say room temperature? I didn't say room temperature, but then given the pressure and volume happening, I don't think this will be any extreme temperature. So in that case, good assumption for 5 degrees of freedom. Like if in an exam, you should probably write down saying we assume we're at room temperature, or like we assume we're not in some crazy limiting regimes. And so gamma is just 5/3. And for this constant, since you know the pressure and volume at every single state point, you can just plug them in, and now you know what gamma is. Picking B or C, it doesn't really matter, because along the entire adiabatic curve, this equation holds and is the exact same constant. So putting in PB, VB, or PC, VC should give you the exact same answer. In fact, I think in the solution they did both, and they found that it's like almost identical to 3 sig figs. So yeah, that's all you have to do. Remember the units. Okay, cool. And that's it. Good luck with the exams.